Okay, so I think we'll start the PA class for today. So I'll be sharing the screen again. Somebody please let me know whether everything is working fine, the screen is visible, and the voice is clearly audible or not. Okay, thank you. Yeah, so again, I welcome all of you to the week 11's live tutorial for the NPTEL course Bioinformatics Algorithms and Applications by Professor Michael Bromiha. So the last class we discussed some of the concepts regarding QSAR and docking, right? So various parameters and concepts and the overall approach of how we do it step by step. We kind of went over that, and we also solved some problems, right? So in this particular tutorial session, I will try to show you one example, just a brief, I guess, application or tutorial application of that. So I think Professor Bromiha, he went over the docking process using the tool Autodock or Autodock Bina, right? I think it was Autodock. So in this one, I'll just show you briefly how you can apply Autodock Bina via UCSF Chimera. So UCSF Chimera is one tool that I have already talked about and demonstrated its various visualization as well as analysis capabilities, right? So we'll go over that, how you can perform small scale docking with that. And then we will discuss some of the concepts. So we'll do that later. Firstly, we'll discuss some of the concepts that Professor Bromiha went over in week 11's lecture. So can anybody remind me what did Professor Bromiha extensively went over in this particular series of lectures for week 11?
Sir, there was a demo regarding Autodoc, and then it was we got the details of programming language and how can we perform the awk programming, and then we have the development of algorithm. So how do we develop the algorithm which is a user friendly algorithm, and how can we analyze how can we make that algorithm easy so that we can analyze our problems and all.
Yeah.
And also that algorithm needs to handle a large set of data and how to classify that data. All of these comes under the development of algorithms.
Yeah, so different, firstly, awk programming and some, I guess, small commands related to the awk programming, which will help you to parse through basically a large file of data quite efficiently. So it's very useful in some cases. And then something related to algorithms, right? So algorithms and their evaluation particularly. So I guess here you will encounter the different terms such as true positive, true negative, false negative, the rates associated with that, right? Sensitivity, specificity. So these are different terms that you will need to understand to evaluate how your algorithm is performing, right? Yeah, so we'll look into that as well. So I guess firstly we should start with briefly recapping what we talked about just yesterday. So firstly we talked about 1D, 2D, 3D, 4D, 5D, 6D QSAR and their kind of importance or significance, right? So QSAR is basically quantitative structure activity relationship, as you know. So it relates the structure of the molecules in this case, small molecules or ligands with their activity. The activity could be, you can think of it in terms of binding affinity, for example, right? And in various dimensions, we see that the complexity can increase one after another. For example, instead of just correlating the activity with some molecular properties like log P or pK, you can further go deeper and you can incorporate connectivity indices. For example, what kind of contacts the proteins and ligands are forming. You can incorporate that, and you can also take into account the structure of the molecule, the 3D representation of the molecules and proteins, right? So that will come under the 3D QSAR part. And then if you even go further, then you can use induced fit models, you can use ligand ensembles, or you can use even solvation models. You can incorporate all of those into kind of more advanced scale or more computationally exhaustive scale of the QSAR models, right? So how do you do that? Basically kind of the approach. Okay, so the approach was basically kind of finding out the descriptor of your small molecules or your ligands first, and then you have to choose the features that you want to select, and then finally you have to relate that to the model, right? And ultimately comes the model evaluation. So the evaluation part It's in the QSR model. It's also in the ML algorithms, which we will look into the several terms that I talked about. But apart from QSR, also we went over molecular docking, right? So molecular docking is one part which comes at the beginning of a computational pipeline for drug discovery, quite useful. So you can do protein ligand docking, you can do protein docking. There are several tools associated with that. As you said, Professor Gomiha went over Autodoc in his tutorial for week 11. So you can go over Autodoc Vina also. If you want to perform protein docking particularly, there are several interesting web tools which are available online. So these are Haddock and HDoc. We can go for those as well. But can anybody remind me what was the primary two elements of docking, which we also call the two bottlenecks of docking? Uh, the most significant element. So there was two part. One was relating to the structure or conformations of the ligand, and another was related to the uh, getting basically the binding free energy or the binding scores, right? So what was that called? It was the firstly the search algorithm, right? The search algorithm, which is the algorithm that generates a range of poses within the binding site for the protein of the protein. And these numerous generated poses, they are assigned a score via something called the scoring function. Okay, so the search algorithm and scoring function are the two primary elements of docking. And depending, and depending on the computational power that you can go for the scale of kind of thoroughness that you want for both of these, right? So we know that for search algorithm, there are several challenges. For example, due to the ligands having multiple degrees of freedom, it's quite challenging if you go for screening of a large library. Uh, so a lot of times what you can do is you can perform rigid docking or maybe keeping some of the bonds of the ligand flexible particularly, but mostly keeping the protein rigid, right? So you can go for that, or you can go for flexible docking where you also try to keep the surrounding amino acids of the binding site, particularly the interacting ones, those flexible also, but that will hugely increase the computational cost. So you have to balance those out in terms of the time you want to take the calculation to be performed and in terms of what kind of power you actually have, right? So you talked about flexible docking and the types of search that is performed. So firstly was systematic search. So that is the most exhaustive one, the deterministic one, where you go for all of the possible options, all of the possible conformations that can be generated for the ligands, but only feasible for low dimensional problems, because higher dimensional problems you cannot have the power to perform using an exhaustive systematic search, right? Then there is something called the stochastic search, which is what is usually utilized in a lot of these programs or tools, and that includes something, for example, simulated annealing genetic algorithm, etc. So it's stochastic, that means it's random, right? So there is a probabilistic approach that is taken into account here. So for example, in genetic algorithm, we talked about that some random poses for the ligand conformations they are generated, and then they are given some sort of scores, right? Some sort of fitting matrix or scores. And usually, if the beta scoring conformations are found, so two of those beta scoring conformations they are taken. Some part of them are taken. For example, it could be the bond or ring information for one, and it could be the torsion angle information from another. So the different parts you can take from the different conformations generated, and you can mix and match those, right, to generate new conformation, which are called child conformation. So that is why it is called a genetic algorithm, kind of taking a inspiration from there. So yeah, those types of searches can be done. And another is the scoring function. So scoring function we talked about, it can be force field based scoring function, empirical scoring function, knowledge based potential scoring function, right? So the force field based is, of course, where you have the potential related to the bonded and non-bonded interaction implemented into the approach, right? So that is what is used in Autodoc and in gold score, etc. We talked about that. We talked about the empirical scoring functions. So empirical scoring functions is where you get the score parameters to mimic experimental binding affinity. So there are definitely some uh, advantages and disadvantages to those as well. The force field based one was kind of one of the major ones, because this is not only applicable in your molecular docking, but also in a lot of the cases, of course, in all of the cases in molecular dynamics simulation also, you need to utilize these force fields because the potential energy are basically what gives the physics part of the approach, right? So here you had the all atom force fields or the coarse grained force fields depending on the scale of the system. So can anybody remember what is the difference between all atom versus coarse grained? For example, which these two are mentioned here, that they can be uh, categorization of force fields, right? So what is all atom versus what is coarse grained? Let's say in a protein ligand system. So basically, the all atom force fields are where you have all of the atoms of the biomacromolecule as well as the ligands explicitly defined using the force field and their interactions. Whereas in the coarse grained part, you do not have the subtlety of defining all of the atoms separately, but you take a collection of atoms and their interactions. You take that as a single component. For example, you can take one amino acid as a coarse grained bead, right? So that is called a coarse grained simulation, which is useful if you want to analyze a large scale system. For example, you are trying to let's say analyze a tumor microenvironment or a cellular system where there would be multiple proteins, there would be lipids, there would be other stuff, right? So in those kind of cases, coarse grained simulation or using coarse grained force fields would be beneficial because if you go for all atom, it will take a lot of time and we usually do not have that kind of power to perform. Whereas in coarse grained, it can be achievable basically, right? Yeah. So we talked about the force field based scoring systems. For example, these are the potentials for bonded and non-bonded interactions. So in non-bonded cases, we know the van der Waals interaction that is represented by this Lennard-Jones potential. We know that electrostatic interaction that is represented by this Coulombic potential, right? Coulombic charge interaction potential. So, and further we talked about knowledge-based systems which is obtained from protein ligand complex in databases such as PDB. There are some advantages and disadvantages. For example, we can use PMF in this particular case. So PMF or potential of mean force. So that is where you take some parameters, such as in this case propensity here, and you relate that to find out some sort of energy difference or binding free energy difference, right? In this case, some sort of free energy difference. So that is called using the Boltzmann distribution formula or the Boltzmann hypothesis to get the energy change. So it is useful in this particular case. Also, it was useful in characterization, as I earlier talked about. Uh, a basically a large, if you have a large data set or a large data file, so you can divide those into several ranges, right? Several sub ranges you can say. For example, if you have the scale from 1 to 20, you can divide from 1 to 2, let's say 1 to 3, then 3 to 6, then 6 to 9, and so on and so forth, right? So these small ranges are called beans, and then based on the population of the data that we have in each bean, you can assign those a particular energy. The highest populations will be the lowest energy, and you can get a relative energy level for all of the data set, which can basically give you the idea about the distribution of the data. So that is also um, that can also be how you can calculate this potential of mean force in a lot of these cases, as is in trajectory analysis. Yeah, so we talked about that. We briefly went over genetic algorithm. As I said, the parents, which are the conformations that are generated, the children, which are the product of the conformations when we take together, take some part of together the parents and you add them to make a new conformation kind of. So that is kind of part of genetic algorithm. Then we define that, then you iterate over that, and that's how we get kind of a best conformation for the search algorithm or genetic algorithm, right? Uh, and then we talked about how we can do some sort of how we can correlate basically multiple factors or multiple parameters to uh, some activity value, and we can have several numeric problems that can be solved with that. So just simple numeric formulas, if you apply those, you are good basically. Yeah. So we went over that, and then we briefly talked about computer-aided drug design, how you go from screening of a large library to finding out a few of the potent hits that are possible through virtual screening, and then simultaneously after that, some admit analysis to make sure that the predicted admit properties are well and good with what it should be for the drug molecule ultimately at the end, and then you go for some sort of molecular dynamic simulation and free energy calculations. Okay, so anybody remembers what is a method for uh, doing free energy calculation of molecular dynamics? So after molecular dynamics, you generate a lot of snapshots, right? For example, let's say in a 50 nanosecond simulation, you are generating 5,000 snapshots, let's say, for example, right? I guess that would come if you save every 20 picoseconds a snapshot. But all of the snapshots you can take and you can perform some sort of free energy calculations, right? So one of the methods that we often mention, that is called molecular mechanics Poisson-Boltzmann surface area, which is just mentioned here, even previous free energy. That is not the most accurate one, but it has a balance of speed and accuracy basically. So if you want to go for even higher accuracy and more computationally costly calculation, then you can go for something called free energy perturbation or thermodynamic integration. So those are also possible, but they take a lot of time and consume a lot of computing power. So oftentimes, even in GPUs, they are kind of hard to do basically. Okay. So a lot of these cases, the researchers, they will usually go for MMPBSA or even another similar calculation, which is called MMGBSA, which is molecular mechanics generalized Born surface area. So that is kind of an approximation of MMPBSA. The PB part and the GB part, they are kind of related there. Okay. Yeah. So we ended, I think, while talking about this particular approach called deep docking. So anybody remembers what it was about briefly? So what this deep docking thing was about? So this was basically, if you want to scale ultra large scale libraries of beyond 1 billion molecules, what you can do is that since you know the if you want to have a machine learning model or a deep learning model of that scale, you need, of course, enough data to train them, right? However, what happens is that for a particular protein, usually in databases such as binding TB, there is limited information of there can be limited information of several already known inhibitors and their binding affinity or activity values against that protein. So in that case, training the machine learning model or deep learning model with that is always not always possible. So that is why these kind of tools can come in handy, where you can basically dock using molecular docking. You can dock only 1% of the ultra large library, while you use the rest of the ultra large library for prediction purposes using your trained model. Okay. So this docking that you did, the small scale docking, that will be uh, fed into the machine learning algorithm or the deep learning algorithm, and that will be trained using that. And finally, you can use that for your docking purpose as well, right? And I talked about how in all of these scales or all of the parts of the drug development pipeline, AI could be very beneficial. Okay. So that was what we ended, I think. So AI-driven synthesis, planning, and clinical trial processes. There are several facets of that as well. So you can look into the slide when I share, and you will get an idea. This particular review you can go through. This is quite an exhaustive and interesting review. I'll try to share it in the shared Google Drive folder also. Okay. Yeah. So now we come to another part, which is kind of on the experimental side. So this is the activity calculations, right? So what is IC50 value? Anybody remembers? What does IC50 stand for?
So it is a value that in that is a that acts as an inhibitor at 50%, or it that at 50. It's something related to 50%, inhibiting 50% of the
Yeah.
protein, I guess.
So it's half maximal inhibitory concentration. So if you look at this particular plot here, so on the x-axis here we have kind of a compound or a particular inhibitor concentration in nanomolar, right? And on the y-axis you have what is called the percentage of remaining activity. So of course, if you have no inhibitor added to the solution, right, then you will have 100% activity, right? If you keep adding the inhibitor slowly, you will see that the activity of this particular enzyme that will drop, right? So the curve kind of looks like this, and at the particular point where the activity remaining, that is around 50%, that is at 50%, so that will be your half maximal inhibitory concentration. So the point where the activity is kind of remaining 50% of the maximum, okay, that is the half maximal inhibitory concentration. For example, here is also a same plot kind of described in a different way. And these kind of plots can also you can have basically something like this: activity percentage of control, and then something added on the x-axis also. And then you can have different time scales, or you can have different compounds, or then different other solutions also that can be added. And then you can compare and contrast what is happening to the half maximum inhibitory concentration overall in the different setups, right? So that's one way you can do. And then this is also kind of the same thing. So here you can also do percentage of inhibition. So if you do the percentage of activity, then the plot will look like this. Okay, so firstly at zero kind of concentration, you will have the maximum activity, 100% activity, and then it will slowly come down with a plot looking like this. However, if you have the percentage of inhibition, so at the lowest concentration, you will have no inhibition, right? So the plot is kind of inverted in a sense. It's not quite the exact same way, but the plot will become something like this. Okay, so here, for example, the different compounds are you can add, and then you can measure out their IC50 using that as well. At what part, basically, the inhibition is at 50%. So you can represent it in various sort of ways. And then there is one other plot that is here. Just wanted to show this. So there seems to be some sort of error in this particular plot. So can anybody find out what is the error here? So in the visualization of this plot, what could be the error here? So remember that this kind of activity plots you can have on the y-axis the inhibition percentage as well as the activity percentage. Okay, um, and it seems that in this particular case we have inhibition. So is the plot correct, or there seems to be something off about it?
Sir, it's it's just stated inhibition. It's not. It isn't stated that it is a percentage or it is a value, concentration, and all. It just says inhibition, I guess.
I mean, okay, so let's just say it is percentage inhibition here. So yeah,
Okay.
that is kind of explicitly should be mentioned here. But the thing is that, see, in this particular case, on the x-axis, the concentration is going from low to high, right? So the problem is that at lowest concentration or at zero concentration of the inhibitor, so you should not have 100% inhibition, right? So this particular case, it should be activity mentioned here. It's not the inhibition, it's the activity. If you see the lowest concentration, that will have the
Okay,
highest
sir.
activity, yeah, and then it will slowly drop from there. So that is also mentioned in this particular note here. I took it from Wikipedia, basically. So it says that maximal inhibition would occur at the lowest part of the curve and minimum at the highest. So yeah, so that is what was the problem on the particular plot. So it should be activity in this particular y-axis, basically. Okay. Yeah, so that was briefly about IC50. So when back to kind of algorithms, so when we try to basically perform or try to build a model, then of course one of the important parts that will come is how the model is performing, right? So the model performance is quite crucial, and there are, as I said, several terms associated to evaluating model performance, right? And one of them is ROC. ROC. Okay, so what does ROC stand for? That is this question asking. In ROC, you need to have a couple of factors, a couple of terms to calculate it, kind of, or not calculate it. It's a kind of a visualization. You can say it's kind of a plot sort of system. But in this particular curve, you can also calculate the area under the curve for the two reaction coordinates or the parameters that you take on the x and y axis. So what does ROC stand for?
Reliability of the curve. Sir? Reliability of the curve.
No, not reliability of the curve. In this particular case, ROC actually stands for this one, receiver operator characteristic. Okay. So yeah. So the receiver operator characteristic is basically what you will have if you calculate two particular parameters. For example, I just show it very briefly. So one will be your on the x-axis, let's say one will be something called FPR, okay, and then on the y-axis, let's say something called TPR will be there, and if you sort of make a plot, so it will go something around something like this, okay, and then you can calculate the area under the curve as well. So what does these terms mean? So FPR and TPR. So this is particularly an ROC curve, okay. What could FPR and TPR mean in this case? So FPR is basically false positive rate. Okay, so this is false positive rate, and then the TPR is true positive rate. Okay, so we will see how the formula works for that as well. So basically, what true positive rate that will mean is that out of all of the positive data in your data set, how many the models can accurately flag as a true positive. Okay, so that is the true positive rate. And simultaneously, false positive rate that will also be out of all of the negative data in your data set, how many the model is flagging as a flagging as a positive, but it should not be positive. It is basically a negative. So that is kind of the downside of the machine or of the model. TPR is kind of the upside of the model. And if you get this sort of area under the curve, so that is one good way to measure how the model is performing basically. So in a lot of cases, the AUC, what is called AUC of the ROC curve. So that is used for evaluating the performance of the model, along with, of course, several other terms as well, right? Now, so based on this particular information, so we have the false positive rate, we have the true positive rate, and then we can calculate the area under the curve for performance of the model, right? Okay, so just based on this particular information, so could you answer this question? So for a random ROC curve, okay, so for a random ROC curve, what will be the area under the curve? So remember that you have the true positive rate and the false positive rate, and then the AUC is in this case they are asking for a random ROC curve. Okay, so what do you think would be the answer in this particular case? Try to figure it out. So area under the curve for a random ROC curve. So in this particular case, the random ROC curve will mean that the model is not clearly able to distinguish between
0.5, sir.
yeah. So
0.5.
yes, 0.5 particularly. So in this particular case, so what is true positive rate? So yeah, the option is correct. It should be 0.5. So can you anybody tell the formula for true positive rate? How can you find out the true positive rate using different terms? For example, it could be true positive, true negative, false positive, false negative, such terms. So how can you?
Sir, it is a true. It is true positive divided by true positive, and I guess true positive and false negative. No, true false positive.
No, it's actually false negative. Okay, so true positive.
I was right the first time.
Yeah. So true positive rate basically means out of all of the positive data in your data set, how many the machine the model is correctly identifying as being positive. Okay, so that is of course true positive rate, and then what will be the true positive? So true positive is basically in your data set, of course, in actuality, the data is positive, and the machine is correctly identifying, model is correctly identifying it as positive, right? False negative, on the other hand, it will be uh, the data on your data set that is positive, but the machine or the model is flagging it as a negative. So in that case, it is false negative, right? So then if you try to find out the overall number of positives in your data or in your data set, so that will be true positive plus false negative, because all of them, all of those represent in total the positive data in your data set, right? So if you have that and you have the true positive, you divide the true positive by true positive plus false negative. That will give you your TPR, or true positive rate. And then what could be FPR? The formula, just if you just similarly try to find out. So in this particular case, it will be out of all of the.
False positive.
Mhm.
False positive divided by false positive plus true negative.
Yeah. So in this particular case, it will be out of all of the negative data in your data set, how many the model is incorrectly flagging as a positive ones, right? So what is the total negative in your data set? So firstly, it will be true negative, of course, the negative data that have been correctly identified as being negative, and then it will also include false positive, because these are the negative data that the machine flagged or the machine assumed to be positive, right? So these will give you the overall negative data in your data set. And if you have the false positive, so you divide basically false positive by this whole negative together, and then you get the FPR, or the false positive rate, right? So then it seems that there is some relationship between true positive rate, false positive rate, and so on. Now, if you have um, a random ROC curve, so what will it look like? So in this particular case, so let's say here I have the FPR, false positive rate. Here I have the TPR. So basically, for a curve or a ROC curve to be random, it will be something like this. It will be a linear curve, okay? And if you get the area under the curve, since the diagonal is equally dividing the whole kind of square or plot, so it will be 0.5, right? So in this particular case, if you see for a random curve, the relationship between TPR and FPR will be this. Okay. So in this case, true positive rate will be equal to false positive rate. So what does that mean? That means that out of all of the positives in your data, uh, the number that the model is correctly identifying as positive, that will be equal to uh, the false positive rate, which is out of all of the negatives in the data, how many the machine is incorrectly, or the model is incorrectly flagging or incorrectly assuming to be positive. So in this particular case, it means that the model cannot distinguish between in what it is doing, basically, right? So for that, for the AUC for a random ROC curve, that will be 0.5. So that means the model performance is random, basically. Okay, so that's what the question was asking. Now, that was your true positive rate and false positive rate. So there are some other terms that are related to this sort of discussion. So one is sensitivity. So anybody knows what is the formula of sensitivity? Formula for figuring out sensitivity using the similar terms that we just talked about earlier.
Sir, it is true positive upon true positive plus false negative.
Yeah, so it's basically the same thing as true positive rate. Okay, so the sensitivity and true positive rate, they are the same. And the formula is, of course, true positive divided by true positive plus false negative, as we discussed, right? And we know false positive rate is false positive divided by false positive plus true negative. Now, there is also one term called specificity. Now, specificity, that has another name, that is called the true negative rate in this particular case. Okay. So the true negative rate, you can calculate it by this formula, where you have true negative divided by true negative plus false positive. So in this particular case, it is basically out of all of the negatives in your data, how many the machine is correctly, or the model is correctly identifying as negatives, actually as negatives. Okay. So the total negative, of course, we see it's true negative plus false positive, similar to what we see in this particular case. FP are also, right, the total negative, TN plus FP. and then you have the true negative on the upside. So that will give you the specificity or TNR. So using this formula, there seems to be some sort of relationship between false positive rate and specificity. So what is the relation between false positive rate and specificity? Just using this particular formula, the formulas that are given here. So you see there is something common in both of these cases, right? False positive rate and specificity. What could that be?
Sir, they are inverse and complementary. That is, false positive rate is equals to 1 minus specificity.
Yes,
FPR.
yes, particularly. So you see in both of these cases, the denominator is the same, right? So it's FP plus TN, false positive plus true negative. So that means false positive rate will be equals to 1 minus specificity if you just try to do this formula, right? So if you have the specificity, that means you can calculate the false positive rate and vice versa. So that was the um, false positive rate and specificity. And then there is also one term called accuracy. So accuracy is determined by this. Okay, so it's basically all of the correctly predicted values divided by all of the positives and negatives. Now, what could that be? If you write it in terms of the true positive, true negative, false negative. So all of the correctly predicted value divided by the positives and negatives together.
Sir, it would be true positive plus true negative divided by true positive plus true negative plus false positive plus false negative.
Yes, yes. So on the bottom, you will have everything. So true positive, true negative, false negative. And on the numerator, you will have true positive plus true negative. So these are the correctly predicted, because the true positive was the correctly predicted positive values and the true negative was the correctly predicted negative values. So all of these can be implemented while evaluating some models. However, in a lot of cases, you will see that people more lean on to um, the ROC curve, basically the false positive rate versus true positive rate, and the area under the curve for that to determine the performance. Because it can happen is that sometimes for classification problems, if there is, for example, some class where there is a minority population, so the data points in that particular class are not that many. So the accuracy can sometimes give you a little bit biased results, basically. So in those cases also, your the ROC curve and the area under the curve for the ROC curve. So that is oftentimes used as the performance indicator, basically, for this particular model. So you can. I also came across one analogy. Basically, let's say in banking kind of systems. So sometimes it's better that rather than correctly identifying all of the accurately kind of identifying all of the transactions, it's sometimes better to see which transactions are fraudulent and basically marking them accurately, kind of. Okay, so in that case, the same analogy can kind of apply here. So sometimes ROC curve is used as the determinant of the model performance, basically. Okay, so that was a bit about the model evaluation. Uh, and then another thing that Professor Gomha, of course, went over, that is called the awk programming, right? So the awk programming can be quite useful if you have some sort of large data sets. You want to parse through that data sets. So sometimes if you just want to extract specific information, right? So it's quite useful to have this sort of awk programming. And in Linux systems, of course, you can have this kind of inbuilt implemented, right? For example, in our cases, let's say we have a trajectory of molecular dynamics, right? So let's say we have a large trajectory of 2 lakh snapshots. Okay. Now for these 2 lakh snapshots, so they are individual frames of the trajectory. So for each of these frames, we can calculate multiple parameters that we discussed earlier. For example, root mean square deviation, radius of gyration, solvent accessible surface area. It could be several other distances, right? Electrostatic distances, contacts, so on and so forth, right? So you see the number of rows in this particular data set will be 2 lakhs because there are 2 lakh frames. And then on the number of columns, depending on how many parameters you want to have in this data set, it can be a lot, right? It could be like 20 30 number of columns even, right? So in that particular case, sometimes if you want to just quickly find out some of the information, for example, what is at the end of the column 1, what is the column 3 stating, right? How many lines we have in this data set, how many rows basically we have in this data set, because sometimes if your calculation has been terminated before it was finished for some reason, let's say your computer had a power outage, right? Your calculation was terminated there. So how many number of lines was in this particular data set if you want to find out where the calculation was terminated. So in that case also you can use the awk programming to just parse through the data file and then give you the relevant information basically. So quite useful. So in this particular case, the question is asking in awk programming which character is used to identify a field or column. So a data set will be comprised of the rows and the columns, right? So in the column, you have the fields or the different parameters that have been calculated. And let's say on the rows, you have the different frames or snapshots for which the parameters are being calculated. So which option could be true here? So in awk programming, which character for a field or column? Yeah, so I say option C. Yeah, so it's correct. It's actually the dollar sign. The dollar sign or the dollar symbol that can be used to identify a field or a column. Okay. Now again, on the similar note, this is asking about if you want to count the number of lines in a data file. As I said, sometimes it could be useful to see how many total number of rows or how many total number of uh, kind of frames that you are calculating your data for. Sometimes it can give you insights into, let's say, if your calculation had been terminated, that I said earlier, and let's say in previously you merged multiple set of separate data sets together, right? Then did you actually get all of the different data sets that you are trying to add on after another? You can calculate the total number of lines in the data set using this kind of commands, right? So it's also useful in that sense to see what you did earlier, whether that was happened or not, the process occurred or not, basically in this case. So sometimes it's useful to know the count of lines in a data file. Okay, so what could be the command in the awk programming for calculating the number of lines? So I see option B. Yeah. So in this particular case, option B was the correct one. I guess we can just try to execute uh, this sort of command on a terminal, okay, to see what happens. Yeah, so hopefully it's visible here. So we can just try to execute these commands one after another and see kind of what happens here. So here, as I said, we can use the awk programming for parsing through and collecting information from the data sets, right? So the data file that I'll be using is this root mean square deviation file. And if you open it up, you will see it has some information. So I believe I already showed this kind of file. This is generated from a molecular dynamics trajectory. Okay, if we just show how the plot looks like corresponding to the number of snapshots. Okay, I think Let me speak here. Yeah, we'll just try to do it. This one here. Yeah, so what it shows is that it shows on the x-axis the snapshots or the frames that have been generated in this trajectory, and then on the y-axis it has the root mean square deviation value. So if you remember when we talked about RMST, we state that it is a deviation matrix where you have to um, calculate the deviation from a certain reference point. Okay, so this will give you the overall structural deviation for a protein. I think in this particular case, you see in the run, so it was kind of slightly fluctuating at the beginning, but towards the end, it kind of stabilized. So that tells us about the convergence of the process. Okay, the convergence is also a term which you encounter not only in simulations, but you also encountered it in the models evaluation also. When the model is converged, you get your output, right? So that thing. Now, let's say if you have your RMST dap.dat file, and let's say on the left hand side you have the frames, on the right hand side you have the RMST value for the frames. If you go to the end of the file, you see that there are 20,000 snapshots in total, right? Now, if you try to calculate using the particular awk command that we saw earlier, so it should be like this, right? So we did the end print nr and then the file name, which is rmst underscore bat.dat. So it shows us 20,001. Now, didn't we see there was 20,000 frames in this particular data set? So what's going on? Why there is extra one that is coming in the total number of lines? So there is 20,000 frames on the bottom, right? But on the top, if you see, there is a hashtag frame and then RMST value, which is kind of not included if you try to plot it due to the hashtag. But it is also, if you just try to use it as a text file, so how many number of lines it has, so this particular line will also be counted towards that. That is why there is a total of 20,001 file, 20,001 lines in this particular data set. If you try to execute the other commands also, so if you do this particular command, so it is print fnr, then a tab, and then colon zero, $0, then the data file. So you will see that the entire kind of data set that has been pasted onto our terminal here. Okay. And now you'll see on the left hand side, the line number is also mentioned. So the line number additionally comes pasted with that. Okay. Now, for example, let's say for somehow you want to save this output also. So what you can do is you can save this output in a other file, which is, let's say we call test.dat. So you can do that also. So in that case, the terminal will not have the information, but you open up the test.dat file, you will have the relevant information there also. So you can save the output of the awk commands in a separate file as well. So that's one thing. So we learned about the column number using the dollar flag, right? So what does $0 mean in this case? So because in your data file, which is in this case rmst.dat, there are two columns to remember. So on the left hand side frame, on the right hand side the RMSD values. So what does the $0 mean here? For example, if you do $1, if we just do this command, you see what is happening. You on the left hand side, of course the line number is being pasted. On the right hand side, what was in the very first column, that is being pasted, right? If you go for $2, on the left hand side again you have the line number being pasted. On the right hand side you will see the RMST value, which was on the second column, that is being pasted, right? So it seems that overall $1 means the first column, $2 means the second column in this data set, So what does $0 mean? No, not space in this case. And it's essentially quite handy if you want to if you want to retrieve some quick information from your dataset. So that's kind of the point. Okay. So you can go through the several online tools. For example, I think I showed you one online website like W3 School or something like that, which had some relevant Linux command information, some relevant Python programming information and commands related to that in simple way. So you can go through those kinds of services or tools, and you can find out more about the awk programming language and how to implement it basically, right? So yeah, as you said, all of you said, it was the option B, which would give us the count of the lines, how many rows are there basically. Okay, yeah. So if you try to solve using all of the formulas that we learned earlier, this particular question, where it is asking that uh, in the following assignment. So assignment is basically your let's say your experimental assignment and the actual and the predicted value by the machine. Okay, predicted assignment by the machine. So that is given here. So in this case, they are asking that B is positive. Okay, so B means positive, and then N is negative. So you have the experimental versus the predicted. So what will be the sensitivity of the model? So sensitivity, if you remember, it was the exact same thing as true positive rate, which was true positive divided by true positive plus false negative. Okay, so could you try to calculate it out quickly? We'll just see in a moment. So what will be the sensitivity based on this assignment given here of the experimental value, the actual value versus the predicted kind of assignment? So, okay, try to calculate it out with this. Just try to calculate how many of them are correctly assigned as positives, and then subsequently with that the false negative ones, right? So how many were actually positive but were incorrectly flagged by the model as being negative, and then you will get the answer. So yeah, let's try to figure it out. Basically. So, so how many of them are true positives? Basically, so true positive means in the experimental set of data, um, we had, of course, the positive value which was correctly identified as positive by the model. So in this particular case, you will see this set of B's that we have here. So they have been correctly identified or predicted to be positives, right? So these are the true positives basically. We have two here also. We have here also. So it seems that the value for true positive, that will be 6, right? As it is mentioned here. Now, how many are false negatives? So false negatives are positive values which are incorrectly flagged as being negative by the model. So one seems to be here, and then another one seems to be here. So there is no other false negative in this particular case. So yeah, it will be 0.75 if you calculate out the sensitivity or the TPR. Now, could you quickly calculate out the specificity of this particular model also? So specificity is true negative divided by true negative plus false positive, right? So now you think in terms of the negative ones. So firstly, how many in the experimental set were negative and they were correctly identified as negative, and how many of those negatives are incorrectly assumed to be positive? So what would be the value here? Just quickly try to calculate it out and then we'll just see. Okay. Specificity would be true negative divided by true negative plus false positive, right? And it seems that, for example, so true negatives are, it would be this one, it would be this one, here, right? 2, 2, 4, then here 5. It seems the number is 5. So 5 true negatives. If you divide that by true negative plus false positives, how many are false positives? You will see the negatives that were identified as positives, right? So it's this set of three predictions. Okay, so these are your false positive values. So yeah, 5 divided by 8, it will be 62.5%. So that's correct. In this case, our original question sensitivity was 75%. That is also correct. Okay. So just for this set of questions, just try to remember these formulas. Okay, sensitivity, specificity, true positive rate, true negative rate, as well as accuracy. So try to remember these formulas because these are kind of simple numeric questions. So remembering the formula is critical because you could quickly easily face this in the quiz also, right? Now there are an other set of kind of calculation if you want to go for that sometimes can lend important insights into different factors, for example. So that is correlation. Okay, so we also saw the correlation can be calculated between multitude of parameters. For example, we learned about the folding rate and the contact order correlation, the folding rate and the long range order correlation. So we learned that those are negatively correlated, right? The correlation can also give you some handy idea about the motion of a molecular dynamics trajectory also in something called dynamic cross correlation. So correlation is quite important. If you see one set of parameter is kind of being related to the other set of parameter in a positive or negative way, so you can find out using correlation calculation. Now, the question is asking, so which of the following equations will be correct if the correlation between two sets of A and B is -1? So this -1 value, that means they are negatively correlated. They are kind of anti-correlated. So if you increase the value of one particular, you know, variable, like in this case A, let's say, so the value of the other one will decrease, and it is vice versa. So that will be a anti-correlation or negative correlation. So which of these can give you the equation for that particularly? So here in this particular case, since it's talking about negative, it will not be option C. In fact, it will be option B. If you see that if you increase the value of B, for example, let's say it is going from 4 to 5 to 6, 7, 8, 9, 10, you will see that the value of A is becoming increasingly negative, right? So that is why in this particular case, the negative correlation will be indicated by this option B. In this case of C, D, you are calculating something like inverse correlation. The value is definitely decreasing, but not in the negative kind of fashion, which is kind of what is mentioned in this in the -1 value. Now, yeah, if you come back to the different models, so apart from the machine learning algorithms, the machine learning algorithms could be a support vector machine, random forest, etc. So Professor Komiha also introduced some of the more advanced ones, for example, deep learning or neural networks, deep neural networks, and so on, right? We saw that the deep neural networks or in neural networks in general, they can be used in, they have been used in a variety of approaches. For example, the deep talking that I talked about earlier, of course, the most famous AlphaFold that is using this sort of deep neural networks for predicting protein folding, right? Conformations of the protein. Then you have the computational protein design by Professor Baker's lab. They also implement the neural networks in different ways. So the question particular here is asking how many number of layers are required in a neural network. So the number of layers are basically critical, and we'll see that if you increase the number of layers in between, you can the model can become basically more complex, and it will be capable of handling kind of more diverse data sets in a way. So, so in this particular case, I see option 2 is mentioned. So the number of layers for a neural network is 3, the minimum number of layers. So if you see the kind of architecture here, of course, you have an input layer and you have an output layer. But in between what is happening, that is a part of something called the hidden layer. Okay, so this hidden layer you have, there are several nodes, let's say they're connected to both input and output layer, and you will see some sort of weight associated between these connections also, between these edges, if you will, right? So the number of hidden layer, at least one you need to have for it to be considered a kind of a neural network. And then the more number of hidden layers you have, the more number of complex kind of calculation or prediction the model can do basically. So that's one thing. You can also kind of change the different weights to get the model better. So that were those are kind of the part of different parameter or hyperparameter tuning and so on. But the minimum number of layers, remember that the minimum number of layers for this one is 3. Okay, so as part of the previous kind of discussion where we talked about the true positive, true negative, false positive, false negative, etc. So there is also something related to that is called a confusion matrix. So anybody knows what a confusion matrix is? So it's basically the same thing, but the true positive, true negative, false negative are outlined in a matrix structure basically. So let's say on this upper axis you have the actual values or the experimental values. Let's say on the left hand side you have the predicted values, and you have the positive and the negative that are assigned in the different parts of this 4 ones, right? So you will have true positives, which are of course actually positive and that have been correctly predicted as positive. So this one we will have similarly other values also, true negatives, false positive, and false negatives also. Okay. So if you are asked to calculate the specificity from this particular confusion matrix, so what will the value be? So just try to calculate it out quickly.
Sir, can you repeat the question?
So in this particular case, the positives and the negatives for actual and the predicted values are represented in a matrix-like structure. So this is called a confusion matrix. Now here you have been given that exact same thing, actual versus predicted, positive and negatives in both sides. So you have to calculate the specificity using this formula that we talked about earlier. from this matrix, from this confusion matrix here. Okay. So what could be the answer here? So basically, just try to find out what is the true negative values, what is the false positive values, right? So the true negatives will be the values that are negative in the actual set and that are negative in the predicted set also. I mean the predicted calculation also. And the false positive will be the values that are negative actually, but they have been assumed to be positive by the prediction. Okay. So from this particular confusion matrix, just try to calculate it out. We'll just see in a moment. And yeah, and I guess for the previous one, when you talked about there being no hidden layer in a neural network, so there is possible that you have a perceptron kind of. So that will have a direct mapping from the input to the output, but those are specifically for kind of simple problems basically. Okay, if you want to go for complex problems, you need to have at least one hidden layer, and then if you increase the number of hidden layers, then you can solve progressively complex problems. But the perceptron can also be there. Okay, direct mapping from input to output. Yeah, but in this case, so what will be the true negative basically? So true negative is it was negative actually. So you focus on this, and it has been predicted correctly as negative by the model. So this 20 value seems to be the true negative one, right? And then what will be the false positive? So I believe this one, it was negative actually, but it was assumed to be positive by the model. So it will be 20 divided by 25. It should be 0.5 basically. 0.5 means 80% here. In this case, in the previous kind of set of assignments, they gave a range answer from 0.75 to 0.85. I guess there's some sort of error margin here. But if we just calculate it out, it should be around 0.8. Right? Yeah. So again, we can solve the same kind of questions, but now in a different format, kind of in a more descriptive format. So it is asking that you have a protein DNA complex and there are 100 amino acid residues for the protein, right? So 15 of those residues, they are binding site residues. They are basically where your protein is kind of bound to the DNA, right? Now you have a prediction program which identified 20 binding site residues and 9 of them are matching with the experimental data. So the experimental binding sites are considered as positive, of course, because experimental data is kind of, you have to think of it as the actual sort of values or the actual data. Okay. So what is the true positives and false positives in this particular case? So the true positive will be, of course, how many of the actual binding site residues are correctly identified by the model. And then false positives will be how many incorrect binding site residues, which are not actually binding site residues, they are being assumed to be positive, or they are being assumed to be binding site residues by the program. So what will be the answer?
Sir, I didn't understand the question quite well.
Yeah, so basically what you have, so you have a protein DNA complex, right? So some amino acids of the protein are binding to the DNA. Okay. Now, what program you have built that tries to predict which amino acids of this protein will be binding to the DNA. Now, you already have a protein DNA complex known, and it seems that for the protein DNA complex that you have, it has a total of 100 amino acid residues, of course. And it seems that 15 of the amino acid residues are actually binding sites. So you have the actual data, you have the actual experimental data of which amino acids are the binding site residues, and the number of that is 15. Okay, so that is your actual binding site residue value. Now your prediction program that has identified 20 binding site residues. So originally you should have 15 binding site residues, right? But the prediction program has
Got it, sir. Yeah, got it.
identified 20 residues. However, it has not correctly identified all of the residues. Only 9 of them are matching with what you originally have as the 15 residues. Okay, so only 9 of them are matching with the experimental set of data, which is the 15 residues that is already available or already known to you. So now based on that, what will be the true positive and the false positive? So you say 9 and 5. Yeah, so exactly. Not 9 and 5, 9 and 11. So 9 will be, of course, the true positives because 9 are matching with the experimental data. So that means that it was actually binding site residues and the program is also identifying it as binding site residues. However, that means that the other 11 amino acid residues, which are the part of the predicted 20 originally by the program, so those 11 residues are not actually binding site residues, but they are flagged as binding site residues. They are assumed to be binding site residues. So that means those will be false positive because they are not binding site residues. Okay. So in this case, 11 will be the number of false positives. So 9 and 11. Okay. So just be careful a bit. These types of descriptive questions, particularly, they can be a little confusing at first. So just think it through, take some time, and then try to find out the answer in that, okay, in your exam. And if you try to see the sensitivity of the method, of course, the sensitivity will be defined as, again, true positive rate. So true positive by true positive plus false negative. Now your true positive was 9, of course. And then what will be the false negative? So basically, if you see, false negative will be the number of binding site residues that are actually present in the binding site, but the machine or the algorithm did not identify them as such. So you see here originally you have 15 binding site residues. Only 9 of the predicted ones are matching with the experimental data. So that means the remaining 6 in these 15 value. So those were not identified by the algorithm as being binding site residues, right? So those have been flagged as negatives, but false. So that is why that is the false negative value here. So 9 divided by 9 plus 6, if you do this 0.6 calculation, like in 60%, so that will give you the sensitivity of the method, again, using the same kind of formula and the same kind of method there. Okay. Yeah. So I think I'll do what I'll do is I'll just quickly try to show you, as I said, a brief implementation of Autodoc FINA. So you can use Autodoc FINA using the Chimera tool. So we have already seen the Chimera tool in a lot of scenarios. We have seen how the visualization works. We have seen basically how you can try to do different calculations using Chimera. And one interesting thing is that, let me just show you the complex. I open it up using Chimera. One interesting thing is that there is also a tool of Autodoc FINA that is implemented within Chimera, UCSF Chimera, basically, right? So here, if you see, so in this particular complex, let's just do a little better preset, if you can see. So there on the binding site, you have this ligand molecule. Okay, if I color it in red, so you'll be able to see it better. So we have in this particular complex the ligand molecule bound to this protein. If you go to this tools bar, and then if you see the surface / binding analysis, you will see that different options are coming here. Okay, one of them is this Autodoc FINA option, which you can use for docking. Okay, so firstly, what I have done is that I have extracted the ligand from the protein. Now we want to dock a new ligand onto this site of the protein. And for docking particularly, you need to generate a sort of grid. Okay, so the grid is surrounding the region where you want the ligand to be docked. Okay, now for that you either need some sort of information of which amino acids are your binding site part, or in some cases, for example, in Schrodinger also, if you have already a co-crystallized ligand or already docked ligand or something like that. So you can use, you can build a grid using the center of mass. You can build a grid surrounding this particular ligand that is already present there. And in the subsequent calculations, of course, the ligand is removed. But the information from the grid comes from the position of the ligand where you want to kind of dock your novel small molecules to, right? Now, in this case, what I did is that I separated the receptor from the ligand. You can just do it via, for example, let's say I select the entire protein. I go action, I go atom/bond, I go delete. So now I have in this particular opened up file only the ligand information, and I can just save it. Okay, I can save it as a new PDB file, and then I can have just the ligand. Then again, I can open up the previous complex file, and then I can delete the ligand and then save the receptor in a different file. So that can work, right? But what that will do is that if I open up, for example, the receptor.pdb as well as the ligand.pdb, what that can do is that it can give us information about the binding pocket. Now, it's possible that I selected the ligand, and then while performing the docking, I deleted the ligand that is already present in the cavity. So that was also possible, but I just did this manually so that when you select the which part is the receptor, which part is the ligand from the toolbar, so there is no kind of chance of error there. Now, what I wanted to do here in this case, if I just show you, so in the preset, I'll just go to silhouette, rounded ribbon. I will open up the file for the ligand that I actually want to dock, which is in this file ligand2.pdb. Okay, so the ligand.pdb, which I opened up here, that was your originally positioned kind of ligand. This is the file. This is the ligand that I actually want to dock in this magenta kind of color or the light pink color. So what I have to do is that we go to tools, we go to surface/binding analysis, we go to Autodock Vina. Okay, so in this particular case, you will see if you expand these options, so all of the necessary kind of calculations are taken care of by itself. So you see that add hydrogens in chimera, so that is as true, merge charges, etc. That is true. Ignore waters, that is true, etc., etc. So the default set of options usually takes care of kind of all of the necessary processes. But in this case, what you have to do, you have to just select one output file. I will just let's say name it output.pdbqt. But here you have to select the receptor and the ligand from your workspace. So if you click this, of course, our protein was named as receptor.pdb. And the ligand that you want to dock, that is actually this one, right? So this is the ligand2.pdb file that we opened up. So you will just select the ligand2.pdb file here. And now thing is that we'll click this resize search volume using button 2. So what I can do now is that based on or taking the position of the original ligand as reference, I can create a grid box here. So I just pressed the scrolling wheel button of the mouse, and then what happened is that it generated a grid box. Okay, now you can resize the grid box. You have to see that some part, you can see that, for example, this particular part is outside of the grid box. Okay, so you can, using again the scrolling wheel button, which is the button 2 in this case, we can resize this so that in all of the directions the box is kind of covering the whole part. For example, in this case, we do not need this big of a box on this side. But overall, what it should be is that in all of the areas for the original ligand, it should cover basically. This grid box should cover, because that will be the search, that will be kind of the space where the algorithm will try to fit the ligand conformations to. Okay. So you see that everything is done. Maybe you can just increase the box volumes by a little bit more on some sides, right? And then you see that if you open up the previous tab that was already opened, it already has the center as well as the size for this particular grid box, okay, where the docking will be performed basically. So now it seems that the original ligand.pdb, which was already there, so that its kind of purpose is done. It just served as a visual kind of positioning guide for the box. Let's check it once more, and then if everything seems fine, we'll just go for deleting this ligand.pdb from here. So let's say residues, not residues. Yeah, we can, I guess, manually select it also. So I will just select this one. Now the ligand is selected. I just pressed an up arrow. Just put to actions atom/1 delete. So now everything is fine. Our grid box is set on the particular position. The ligand that you want to dock is also in the workspace, which is already selected in this Autodock Vina kind of toolbar or the tab that was opened. There are some options, number of binding modes that you want to calculate, the exhaustiveness. You can play around with these options to see what kind of information you get. And now ultimately, you have to give the path for the executable. Now it happens that I downloaded the executable file for the Autodock Vina here. So you can, of course, go through the Autodock Vina website, and then you can have their executable. I guess you need to submit some sort of registration, some sort of information regarding your affiliation, institute, and so on, name, email address, etc. So then they will gladly give you the files for the Autodock Vina. So it will look something like this. I extracted it. There is some sort of license information here also. Okay. And then in this green file, kind of, there is something called Vina. Okay. So this Vina, this is an executable program. You see it's highlighted in green. Okay. So usually that means that it is an executable program in Linux. But if you have the path of this, you will see that it's in this particular path, /home run the software and the Autodock Vina _112, then bin. So the same thing I have selected it here. So it was not previously there. I just copy pasted it earlier. So that's why it's still showing the exact same option. And then you have to give the executable Vina. Okay, finally. So now with all of this setup, you can just press OK, and you will see some output file is being written here. And then the calculation will seem to be running. Okay. So let's just see what kind of result it gives us. And based on that, you can select whichever docking pose that you can take to your future calculations. Okay. Yeah. So that was a quick calculation because it's only one kind of small molecule, right? So it does not take that much time if you have decent CPU in your system. So the original ligand that we opened up is still in the workspace, but we do not need that. You will see on the binding site of the protein now the different conformations for the ligand has been generated, and we also see the different poses for that also, right? The different scores associated with those also. So if we select all of the conformations together, this is something that it looks like. So all of the conformations are here, slightly different, each one slightly different. For example, if you go for the 7.4 versus 7.1, the orientation has changed. I guess the cavity, some part of the cavity is here also, so it is shifting towards there. But in the case, in this particular case, you have all of these scores, and the best one is the minus 7.4. Okay, the minus 7.4 docking score. So this should be in kcal per mole, and the base binding free energy that you're getting from the docking calculation. Okay. So the lowest one is minus 6.7. You can go through the conformations to see what sort of structure they have, what sort of orientation they have. And then the RMSD value that is calculated here with respect to the best docked pose for the other ones, okay, for the other kind of ligand poses. So that's why in the case of best docked pose, you have the RMSD values as 0. Whereas in the other cases, you have some sort of RMSD value. So I guess it will be either heavy atom RMSD or including the hydrogens as well. But that's why you have these different values here with respect to the base docked pose, right? Since it's a 7.4, that's a good docking score. So you can take this conformation as your future kind of calculations, for example, in molecular dynamics simulation. So what you can do is basically you can go to file, you can go to save PDB, and you can select which particular structures you want to save the PDB as. For example, here I have the receptor.pdb, and which of the poses that I want to save. So if you go back to the tab, you will see that yeah, so I believe it's in point, right? So this 1.1 hashtag 1.1, that should be the first one, right? The first post that we have in this particular case. So if you just select that one with receptor.pdb, just in a separate file, so you will get your docked complex structure that you can use in simulations and so on. Okay. So if you quickly visualize the surface of the protein, what the cavity kind of looked like, you go to action, surface, and show. It's simple. It will show you the surface, and then it looks something like this. See, there is a cavity here in this particular protein, right? So in this cavity, the ligand is residing basically. If you go for the other conformations also, you will see the kind of position shifting slightly. For example, it went to this particular place. Okay, so I guess it was from a deep cavity to slightly shallow cavity. Some parts of the ligand is moving, so that's why the docking score is reduced in this particular case. It could be different reasons, could be context taking, different context forming, and so on. So that could be the reason for the different docking scores. But anyway, you can take this sort of structure for your further calculation. So that's basically it. Okay. So yeah, utilizing Chimera is quite a useful. It's a useful tool to know. Apart from docking, we know you can perform several other calculations, visualization, distance calculation, hydrogen bonding calculation, contact calculation, etc. You can do the different preparations, for example, hydrogen addition, charge calculation, etc. You can even perform minimization for proteins or for protein ligand complexes using the different tools. So a range of calculations are there. If you have a trajectory, you can view the trajectory as a movie, which can tell you about what kind of conformational changes are going on in your system. Multitude of calculations, basically, if you try to play around with them, you will get to know all of the relevant ones that could be useful to you, basically. Okay. So that's just a small demonstration of molecular docking using the Chimera implemented Autodoc Vina. So Autodoc Vina, they have their website. If you go to their website, you can quickly find out how to download these tools, download the software separately. You can go to the Chimera server or Chimera website also, and you can download their software also as well. Okay. Yeah, so I think for today, I will just wrap up the session here. So that was all that I wanted to discuss here, the algorithm part, and then this brief kind of view of the Autodoc Vina implemented in Chimera and the docking process with that. I guess if I can, in one of the later classes, I will try to show Autodoc as well in a Windows system, if that's possible. So we'll see what happens. Okay. So yeah, I believe I'll just wrap up the class right now. So thank you all for joining. There is a session tomorrow also. So try to attend that one. So go to Professor Gomiha's lectures very carefully. And as I said, the questions should be similar to what you have already experienced in the assignments and what Professor Gomiha has gone over in the lecture series videos. So try to just get the fundamentals of those, and whatever needs to be memorized, for example, the formulas in the algorithm evaluation. So try to keep those in your mind as well, and you should be quite good to go. Okay. So yeah, so thank you all for joining, and we'll see in the next one.
Thank you so much, sir.
Yeah.